Hello everyone, this is Vasant, a nine-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to discuss about composite beams. Why this topic is important? The composite beams have many applications in daily life. You can see bimetallic beams. They are composite beams because they are made up of two different type of materials. Plastic coated beams, wood beams with steel reinforcing plates, etc. And in recent times, composite beams are used to save material and to reduce the weight of the structural member. For example, sandwich beams. In sandwich beam, this is the sandwich beam. See, at the edges there will be thin plate which is made up of one type of material. This will be of high strength. You see in the middle portion. In middle portion, it will be made up of another type of material which has low strength and lower weight. Okay. So because of which the weight of the material will reduce and it will save the material. So this is bimetallic beams, which has thermal applications. So we already discussed about homogeneous beams made up of single material. Now we are going to deal with homogeneous beams made up of two different homogeneous materials. Okay. So see, if you see the cross section of the beam, suppose the cross section is something like this. So here it is made up of one type of material with value E1. This material is homogeneous in itself, and this material is also homogeneous and isotropic in itself. So it has Young's modulus E2. Okay. So first, in homogeneous beam of single material, we found out that the neutral axis will be at the centroid of the cross section. But in composite beams, where will be the neutral axis? We need to find out location of the neutral axis. So that is pretty obvious. Same method. The net longitudinal force on the cross section must be 0, because here we are not applying any axial loading. We are just applying pure bending, right? So in axial direction, there is no force. So the net force developed by these movements, the normal stresses developed by these movements, due to these normal stresses, whatever force, net force should be there, that should be 0. Okay. So we can say that, suppose this is the neutral axis, neutral surface wala axis. Okay. So then this is the neutral axis and this is y axis. Okay. So we can say that from this axis, if we take a small element of area dA, and here there will be sigma x1 into dA integral over material 1, this one will give us net force on the material 1, right? And similarly, we can write integral, if you take small dA in material 2 and this has distance y from the z axis, then sigma x2 dA integral over material 2 will give the net force on material 2. So sum of these two forces must be 0, because there is no axial force applied on the beam. So this must be 0. And we know that sigma x1 will be is equals to minus E1 into kappa y if the material is linearly elastic. Okay. So for linearly elastic, it will be minus E1 into kappa y. So and similarly, sigma x2 will be is equals to minus E2 into kappa y. Do you agree? So one doubt over here is that whether the radius of curvature for both materials will be same or not. It will be same, because if you take this duster and you attach a duster of another material over here, and if you try to rotate like this, these two materials rotate rigidly, means these two materials rotate with attachment, right? So dono ka radius of curvature will be same. I can say like this. See, if there is material like this, and this is one type of material and another type of material is attached to it. So when you apply moment M and moment M like this, then they will go like this. So this is something similar to that compound bar which we discussed in axial loading case, right? It will go like this. So दोनों का radius of curvature in pure bending will be same. Okay. Suppose this is neutral axis. So from the neutral axis we will measure the radius of curvature. So the curvature will also be same. So we can write for sigma x1 is as this value and sigma x2 as this value, right? So if we put sigma x1 and sigma x2, we will get this one, as kappa is common and constant for pure bending case. It is constant for pure bending case. So we will get this value. This. So if you see over here, this is first moment of area of material 1 from neutral axis, right? This is first moment of area of material 2 from neutral axis. So E1 multiplied by first moment of area of material 1 plus Young's modulus of material 2 into first moment of area of material 2 should be is equals to 0. From this we can find out the neutral axis position. So we can't say directly where the neutral axis will present, but in case of homogeneous single material case, we say that centroid will be the centroid of the cross section will be the neutral axis. So we can directly say here there will be neutral axis. So this is the formula for finding out neutral axis. Okay, this gives location of neutral axis. Now, moment curvature relationship. In homogeneous beam with single material, the moment curvature relationship is kappa is equals to 1 by rho is equals to m by ei, right? So this is single homogeneous material case. Homogeneous and isotropic दोनों चाहिए. Isotropic material case. And this is flexural rigidity, right? Flexural rigidity. This we derived from the point that the moments created by the normal stresses developed due to the bending moment at that cross section should be is equals to the bending moment at the cross section, because of that bending moment the normal stresses are developing at the cross section. So whatever moments created by these normal stresses, that should be is equals to the bending moment at the cross section, right? That is simple. So that will be given by minus integral a into sigma x by dA, because if you take dA element and this is neutral axis and this distance is y, sigma x dA will give us the force into y will give us the movement. So integral over the area will give us the net movement, right? So this should be splitted into two parts. One is of material 1 and another is of material 2. So that will be something like this, right? We know the value of sigma 1 and we know the value of sigma 2. That will be minus epsilon, sorry, E2 kappa y. This is minus E1 kappa y, right? So from this we get the values as something like this. The radius of curvature, curvature is same for both. So we can write m is equals to kappa into E1 I1 plus E2 I2. So we get kappa is equals to 1 by rho m by E1 I1 plus E2 I2. So this one represents the flexural rigidity of this composite beam. So flexural rigidity of composite beam is E1 I1 plus E2 I2. Okay. And this is bending moment at that cross section. In pure bending case, the bending moment will be constant, right? So constant bending moment, and E1 I1, E2 I2 are constant for a prismatic bar. So the radius of curvature for a prismatic pure bending case will be constant, right? That will be constant. Okay. So this is moment curvature relationship for composite beam. See, for homogeneous single material beam we got like this m by ei. For this m by E1 I1 plus E2 I2. Okay, it makes sense. So this E1 I1 plus E2 I2 is the flexural rigidity of the composite beam. Now normal stresses. See, in case of homogeneous beam of single material, we get normal stress sigma x is equals to minus my by I. Don't bother about the sign. So we get as this one for homogeneous isotropic single material beam. So now we are going to derive normal stresses for composite beam. If you see that material 1, we know that sigma x1 is equals to minus E1 kappa into Y. So x1 minus E1, what is the kappa? We already derived the value of kappa, that is m by E1 I1 plus E2 I2 into Y. So from this we get sigma x1 is equals to minus my E1 divided by E1 I1 plus E2 I2. See, what is I1 I2? I1 is the area moment of inertia of material 1 from neutral axis. The axis is neutral axis only. For I2 also, the area moment of inertia of material 2 with respect to neutral axis. Okay, the axis is same for both. So first we need to find out the neutral axis. From that we can find out I1 and I2. Okay, from that we can find out the curvature with if we know the bending moment. So from that we can find out the normal stresses. So this is sigma 1. Similarly, sigma x2 will be is equals to minus E2 kappa into Y, right? So we get minus E2 into m by E1 I1 plus E2 I2 into Y. So from this we get minus m by E2 divided by E1 I2 plus E1 I1, which should be I1 plus E2 I2, okay? So this will be sigma x2. So this part is common for both, that is kappa, okay? So it will vary with YE2, it will vary with YE1. So if you draw the diagram, suppose this is the front view of the cross section, and see from here there is material 1, and from here there is material 2, and we found out this is the neutral axis, suppose, okay? Neutral axis. So from here, if you go like this and the moment applied is something like this, then upper walla will be in compression and bottom part will be in tension, right? So the diagram will be, so this is material 2, right? So if you see the diagram here, the variation will be given by E2Y, kappa into E2Y, right? And it is in compression over here. So it will be in compression, okay? And the slope will be E2, right? Kappa E2. And if you see over here, this is E1, okay? The variation will be E1 into Y. So suppose the slope of E1 is somewhat less, then it will be something like this. And this is also in compression, okay? Now this will be in tension. So again with same slope E2, there will be tension. Kappa into E2. This is kappa into E1. So the diagram will look like something like this. Here it is compression. Here it is also compression, and here it is tension. Okay. And this is given by sigma 2 is equals to minus kappa into E2y. This is given by sigma 1 is equals to minus kappa into E1y. But if you see in the case of homogeneous isotropic single material beam, you will get a single straight line, right? So these have single straight line. But this is not the case with the composite beams. So that we only dealt with composite beams with two types of materials, but there can be composite beams of more than two types of materials also. That is not in our syllabus actually. So with this, what are the important formulas? For first, we need to find out the neutral axis. So the neutral axis can be found out from E1 integral 1 y dA plus E2 integral 2 y dA is equals to 0 for neutral axis, okay, for NA. And after that, we need to find out kappa. Kappa is given by m by E1 I1 plus E2 I2. And after that, we can find out sigma x1 is equals to minus E1 kappa into y, sigma x2 is equals to minus E2 into kappa into y. So we can put the value of kappa and find out the normal stresses. So these are the three important sets of formulas for composite beams. Okay. So this is one type of method to solve composite beams. There is another type of method which is known as transformation method that we will see in next lecture. If you like this lecture, do subscribe to our channel 9pointer. Thank you.